Okay, so this is going to be now the conclusion of the CAPM Lab. So right now you should have 15 data tables in position time, X versus T. You now have 15 data tables in velocity time, V versus T. And now what we're going to do today is we're going to create the velocity versus time graphs. And we have to be careful on how we look at our VT, V as in Victor, our VT data in order to graph the VT data appropriately. So as we can see here in this sample, we see that the velocities, typical start off at 0, 0. The first second goes to 2 centimeters per second. The second, it's 12 centimeters per second, 21 in the third. And then it starts to decrease. It starts to slow down in the fourth and the fifth second. So what you want to do with your data is you want to look at the same thing, look at where the data is trending. You want to plot all the points to the highest velocity that you have. So in my case, the highest velocity is 21 centimeters per second at 3. So, just to keep it simple, just plot your points, just like you would in algebra. 0, 0. We have 2, 1. We have 12, 2. We have 21, 3. And then we go 7, 4, roughly, kind of approximate it right there. Fourth second, 7 centimeters per second. And then 2 centimeters per second at 5. So just make it rough. If you have graph paper, great. You don't have to be, technical about that, because at this point it's very trivial. Just get a best fit graph for your best fit lines and all that good stuff. So how are we going to go from velocity to acceleration? But before that, okay, make sure that you've drawn your best fit lines, your line of best fit that goes through 0, 0, of course, 2, 1, 12, 2, 21, 3, and so forth. So your line is going to go, it's going to be an increasing line all the way to your highest velocity, which in my case is 21. In your case, the velocity could be the highest in the first second, and then it starts to decrease from 2 to 5. It could be the highest at 2, 3, and 4. Probably more than likely not at 4, but just going to get all the possibilities that we have for 5 seconds. And I'll show you a couple of more examples of that after we get the first acceleration data. Okay, so plot your points. If you have a graph that looks similar to this, where your highest velocity is at the third second, plot that point and then start to, draw the line going backwards, going the other direction through the fourth and the fifth second. Okay, so how do we get the acceleration? Because the point of this lab is to, calculate the acceleration of the car. It is speeding up, but at what rate? That's basically what acceleration is. It's the change in velocity over time. And therefore, it's the slope of the VT data. This VT graph that we have, we're going to be taking 2 slopes. We're going to take the slope of this line going up from 0 all the way to 21, and then we're going to take the slope from 21 all the way down to 2. So let me write this up. So just like before, where we stated that the slope of a position time graph is the velocity. Well, in this context now, the slope of a velocity time graph is the acceleration. It's all slopes, it's all algebra being applied physically. So we just have to, over time, hopefully right now, you can see the application that you saw back in algebra with y versus x. Now it's v versus t. It's the same idea. We're just doing physics with it. So the slope of a VT graph, slopes, multiple in this case, the slope of a VT graph is the acceleration, the rate at which you speed up. So when you put your foot on the gas or the brakes, because the gas is going to accelerate you, the brakes is going to decelerate you or slow down. The rate at which you're applying your foot per se, right, is the rate at which you're speeding up or slowing down. So the equation for acceleration, A, because with an arrow, it's just indicated it's a vector, it has a size and a direction. Acceleration is delta V over delta T. Very similar to M equals change in Y over change in X. You should be familiar with that point slope or that slope equation. The acceleration equation and the velocity equation are applications of the slope equation that you see arbitrarily in algebra. Over and over again, cannot overstress that these formulae, acceleration and velocity, they are slopes of some particular relationship. In this case, acceleration is the slope of velocity versus time. Change in Y over change in X, which we don't say change in Y over change in X, we say delta V, delta T, because we know that V is in the Y-axis and T is in the X-axis. This is a slope equation applied physically. That's why we can say the slope of a VT graph is the acceleration, or I say it, just to keep it simple. But so this is going to be delta anything. Remember, delta anything is final minus initial. VF minus VI, TF minus TI, delta V over delta T. Okay. So let me take the slope of the first part of this graph. Guess I'll just expand down here, keep it same page, same view. Okay, so we know that time is moving forward, and so therefore this is going to be our final point in velocity, 21. So take this formula and find the acceleration from 0 to 3 seconds. It's speeding up. There is an acceleration here. It's going from 0 to 21 centimeters per second in 3 seconds. This is acceleration, speeding up. And here is deceleration, slowing down. And you can clearly see it slowing down because it's going from 21 all the way down to 2. We are slowing down here. We are speeding up here from 0 to 3. And then from 3 to 5, we're slowing down. The cart, you gave it an initial push, it sped up, and then after about 3 seconds, generally from what I saw from your data, the cart slowed down. So let's take the acceleration or the slope from 0 to 3. So final velocity is 21 minus initial velocity of 0 divided by 3 minus 0. And that gives me 7. I can get the units here, meters per second divided by seconds. So that's going to give me, go down here. That's going to give me positive 7 meters per second squared. The units of acceleration are meters per second squared. Meters per second, meters per second squared. In this case, centimeters per second squared. Keep my units consistent. But centimeters, meters, doesn't, any type of meters. So 7 centimeters per second squared in this case. So that is my acceleration rate, or the rate at which I'm changing my velocity from 0 to 3 seconds. In other words, that means that every second, my velocity on average is increasing by 7 centimeters per second. Every second. This is what this says. The rate of acceleration, or the rate of velocity change, technically, is 7 centimeters per second squared, 21 divided by 3. So this is the value of the acceleration from 0 to 3. Now we have a deceleration. So pretty much in all of your data for all 15 of these velocity time data tables, you're going to have two accelerations. You're going to have one positive and one negative, right? This is a negative slope. Here is positive slope, positive acceleration. Negative slope, negative acceleration or deceleration. Let's go to continue. So at 5 seconds, this is my final velocity, if you will, is going to be 2 minus 21, because I'm going from 3 to 5. That's my point of, I'm taking the acceleration between this common point, 0 to 21, and then 21 down to 2. This non-differentiable point there. But anyway, you'll learn about differentiability when you go to calculus, yada, yada, yada. All right, so 2 minus 21 divided by 5 minus 3. That's my time interval for the car to go from 21 centimeters per second down to 2. So again, this is centimeters per second. So that's going to be negative 19 divided by 2 centimeters per second. And that's roughly negative 9.5. Negative 9.5 centimeters per second squared. So that's a deceleration. Why deceleration? Because this is an acceleration in the opposite direction. You're putting your foot on the brakes, or the ground is causing the car to slow down. Friction is going to be going the other way as the car is still going forward, but it's slowly coming to a stop, slowly coming to rest. That's what the negative sign means, that the acceleration goes opposite your motion, and the positive sign is going with it. Everything, you put your foot on the gas, acceleration and the velocity same direction. So these are my sample acceleration and my sample deceleration. So what you're going to need to do for your 15 sets of data, again, determine where the highest velocity is. You will then be taking the slope from the lowest to that highest, and then you're going to go from the highest down to the lowest. You're going to see a trend in your velocity data where it's going up, and then it's going down. You have to look at your data and follow this example to get your accelerations and decelerations, your positive and negative accelerations. So this is just a model. So please use this to get your accelerations in all 15 data tables. Okay. So that is that for this example. 7. We have our values 7 centimeters per second squared and negative 9.5 centimeters per second squared. Now let's go ahead and put that into a data table. Our final data table is the acceleration data table. Acceleration measured in centimeters per second squared. Time in seconds, always. So at 0 seconds, it's going to be a little bit different here. But at 0 seconds, the acceleration is going to be constant at this rate, 7 centimeters per second squared, from 0 seconds all the way to 3. Why do we know that? Because this slope is not changing between 0 and 3 seconds. Since the slope doesn't change, the acceleration doesn't change. Why is that? Because we know that the slope of a VT graph is the acceleration. If the slope, since the slope does not change in this VT graph, the acceleration doesn't change. So the acceleration is going to be constant from 0 to 3 seconds. This is why we're going to place positive 7 at 0. and it's going to go all the way to 3. So we can do a little arrow like that to say that it's constant. That value, that slope is constant from 0 to 3 seconds. Hope you guys are tracking that. We will have further questions in class if necessary. But that is it. It's from 0 to 3 seconds. The car is accelerating from at 7 centimeters per second squared from 0 to 3. 0 to 3 seconds. And then from 3 to 5 seconds, basically at 4 and 5, there is a deceleration, negative acceleration of negative 9.5. So negative 9.5 here. You can write it again if you want. It's only 2 values, and you just draw the arrow. So that just basically says from 0 to 3, we have a constant acceleration. And then from 4 to 5, we have a constant deceleration. But here's a turning point here. This is that non-differentiable point at 3 seconds. So we're going to be very technical in the graph. But basically, this is what's going on. Okay, so we go here and do that. So let's now graph the acceleration, right? So just like before, x t data, x on the left, time on the right, 0 to 5 seconds, velocity on the left, time on the right, acceleration on the left, time on the right. We have our independent variable on the left, our dependent, get those always backwards. Dependent variable on the left, independent on the right. Time is always going to be independent. It's something that we just record, never manipulate it. It is the independent variable. So now let's go ahead and graph. Time in seconds, acceleration in centimeters per second squared. Now I want you to label your graphs just like this. Put the symbol and the units that it's measured in, acceleration measured in centimeters per second squared, time in seconds, no shortcuts. Okay, here's 0. So 1, 2, 3, 4, and 5. Okay, so we have a value of, I'm going to extend this because I got a negative. Right, so all the way down like that. And the 7, again, it's arbitrary. That doesn't matter where it goes. You can put, say, roughly there. Fine. So 7, and then we're just going to draw a straight line because it's constant from 0 to 3. That's the graph of your acceleration. It's in the positive domain, positive y-axis. That means it's going towards the east as your car is going to the east. If your car was going to the west and it was accelerating, then the acceleration would go to the west. So that's 0 to 3. And then what we can do from 3 to 5, because this is the point where it turns and goes to, like, say, it starts to slow down at negative 9.5. So we can do something, I forget what it's called in math technically, but it's basically the point where we designate the non-differentiability, the what do you call it? The unknown, or the what is that term? Anyway, there's nothing here. It is undefined. That's what I'm looking for. So this is the undefined point at 3 seconds. And so we're going to go a negative 9.5 from basically 3 all the way to 5. That's how we designate that turn from at 3 seconds. There's no way you can take the slope of that. It's all just rise, right? If you have just run, no slope, rise, no slope. And moreover, there's just nothing happening here. This is just a point. That is just a point at 3. You can't do nothing with the point. You can't take a slope of a point. It's non-differentiable or undefined, or all those terms that mean the same thing. Similar things. So that's your acceleration. So again, you're going to have to look at all 15 velocity tables. I was going to do example of your velocity going from 0 to the highest velocity being at 1 second and everything falling back down. I don't want to make this video too long, but just want to just stress the points just made. 15 of these data tables, right? Velocity versus time. And this is my sample. In my sample, my highest velocity peaks at 3 seconds, then it starts to slow down. Yours might peak at 2, might peak at 1. I saw some data that was peaking at 1, and then it started to slow down from 2 all the way to 5. So be careful. Determine where your velocity is the largest. Plot the points. Go to the highest point, whether it's at 3 seconds, 2 seconds, 1, or 4. And then draw your best fit line up to that point, and then draw the slope going the opposite way from the highest point. Again, in my case, the highest point is 21. Yours at 3 seconds. Yours is probably going to be at some other second. But I did see a lot of data where the highest velocity was at 3 seconds. That's kind of roughly average, for our context, for the amount of friction that we have the outside, just all these little factors. It seems to be consistent year after year that it starts to slow down at the 3 second mark. Just depends. No magic to that. Once you have plotted this V versus T, take the slope, right? You're gonna have 2 slopes, one that's positive, one that's negative. This is a positive acceleration. This is a negative acceleration. We call it deceleration. Why do we say that? Because we understand that the slope of a VT graph is the acceleration. A is delta V over delta T. This is our slope formula for the physical or the physics quantities that we have, velocity and time. Very similar to the slope equation. It is exactly that logically. First acceleration, in my case, at the highest point, I'm just going to go to the, where the graph is going to be positive, where the slope is positive. And so the highest point for that positive slope is 21 for me. 21 centimeters per second minus 0 centimeters per second, right? You get the idea. 21 minus 0 centimeters per second divided by 3 minus 0 seconds, 7 centimeters per second squared. Units of acceleration is some form of meter per second squared, in this case, centimeters per second squared. Then from 3 to 5, my final point in velocity is 2. My initial is 21 centimeters per second divided by 5 seconds minus 3, 2, right? 2 minus 21 divided by 2, negative 19 divided by 2 is negative 9.5 centimeters per second squared. Every one of your graphs should have 2 accelerations, one that's positive, one that's negative, because we start to speed up and then we start to slow down. You can check out the CAPM sample posters in the class. Everything's consistent with what we want for this time interval. I did see some data though, okay, glad I remember this, where there was, for some peculiar reason, the car sped up, then slowed down, and then sped up again. That's kind of false data. What I have to say, I mean, we're gonna have to deal with that appropriately. I don't want to divulge or go off on a tangent on that too much here, but that cannot work. I did see some people outside or inside that were kind of like they let it go and they pushed it again. So that could only be the explanation for that, possibly, or you're taking the data down inaccurately. It's just physically speaking, it doesn't really happen, not unless you did have some kind of pebble or rock or something that sped it up considerably, but kind of highly unlikely. So we're going to have to be careful. Whoever that applies to is going to have to be very careful. But for the most part, your data should look like this, where it speeds up and then slows down. So if you have an extra point that does this, which I did see, kind of not gonna buy that without an explanation. You're gonna have to tell me, honestly, what went wrong with that, because quote unquote wrong, because it just doesn't that doesn't happen more than likely. So something screwy went on with your group. Some people were not paying attention. Something your data is going to give me an indication that something was not done carefully. So be mindful. Most of your data should look like this: speed up, slow down. So you're going to take the slope. Okay, 2 slopes, 1 positive, 1 negative. Once you have those slopes, in my case, 7 and negative 9.5, I'm going to state that from the time that it was the positive slope, from 0 to 3 seconds, that was a positive slope. The slope didn't change. The slope was going to be 7 centimeters per second squared from 0 to 3. Again, because the slope of this line here will not change from 0 to 3. So that means that my acceleration, which doesn't change, is going to be the same from 0 to 3, which is why I put the data in the table like this. From 0 to 3 seconds, it's 7. From roughly 3 to 5, negative 9.5. And then after that, I graph it. So this is my positive domain, positive 7, constant. It's not exactly, but you get the idea. So this is straight line, constant acceleration from 0 to 3, undefined at 3. There's a switch going from the gas to the brakes, that instant. And then from 3 to 5, it's negative 9.5. So that's what you should have for all 15 data sets. You have 15 velocity time data sets. You're going to need to now generate 15 velocity time graphs. You're then going to be taking 15 pairs of accelerations. For every velocity time graph, you're going to have 2 accelerations. You have to determine what time interval that the acceleration was positive and what time interval it was negative. Positive slope, positive acceleration, negative slope, negative acceleration. Pay attention to the patterns. They come back over and over. Okay, so again, 0 to 3, 7, 4 to 5, negative 9.5. I got my acceleration data tables. You're going to have 15 of these acceleration time data tables, and you're going to have 15 acceleration time graphs. So that should be enough for you to do in the 90 minutes class that we have. The thing that we make this too long. Last thing I would like to do is let me get some standard deviation, but we can talk about that in the classroom. This first things first. Okay, get your velocity time graphs, right? You have your velocity time tables. The graphs, 15. Take 15 slope pairs for every graph. You're going to have one pair of accelerations, so 15 pairs. You then are going to populate an acceleration time data table and then make 15 acceleration time graphs. So that is it for now. Talk to you later.